In the name of God, hello everyone and thanks to the jury for accepting our paper. The title of our paper is Multi-Layer Collaborative Graph with BPR Similarity Embedding for Recommender System, which is an issue in the field of recommender systems. The purpose of recommender system is to predict the score or priority that a user will assign to an item, which lead to reduce the complexity of online search and help users to make better decisions. Challenges in recommender systems. Sparsity. Users usually rate a small fraction of the all available items, resulting in a sparse dataset. This degrades the accuracy of the RS because it complicates the process of finding similarities between users as the number of common items becomes relatively small. Cold start. The cold start problem occurs when too little rating data is available in the initial state. The recommendation system then lacks data to produce appropriate recommendations. Two cold start problem are new user problem and new item problem. So our purpose is to learning high-level representation for users and items to deal with these two challenges. Since data in RS inherently has graph structure, the graph neural networks (GNN) have been widely used for feature extraction of RS. From the methods presented in the field of graph neural networks, we choose graph convolutional networks. Graph convolution operation on graphs can be considered as a generalized structure of two-dimensional convolution operations. The overall structure of proposed model is based on GACSE model, but with two main differences. Unlike the GACSE model, which uses only one layer, our proposed model uses multi-layer structure in order to expand the range of neighborhoods employed in the propagation process and increase representation power of embeddings. Due to the high capability of BPR in helping model to identify positive and negative cases, while maintaining the network's ability to offer new items to users, instead of equation used in the GCSE to obtain similarities between nodes of the same type in graph, we use BPR to extract this type of feature as well. The proposed model has three main parts. The first part is embedding propagation layer, which has several sublayers. These sublayers are responsible for propagating and aggregating feature vectors, taking into account the equal weight for node in the user's or item's neighborhoods. The initial sublayer in this section is used to map one-hot vectors which are obtained from the user-item interaction matrix to initial embeddings. The next part is attention layer, which uses the attention mechanism to assign different weights to the embedding of neighbors according to their importance in aggregation process. The last part, called the prediction layer, concatenates the feature vectors from the initial embedding layer and the attention layer, and produces the final embedding related to the user or item. The feature vectors generated in each of the sublayers extract different levels of information through the interaction in the graph. For example, the vector generated in the first sublayer considers direct interactions between user and items, or in other words, one-order neighborhoods. And the embedding generated in the second sublayer contains information related to user and items that have interacted with same item and users, respectively. In the same way, by increasing the sublayers, a higher level of information is obtained from the exciting relationships. We propose a loss function with three parts to train our model. The first and second section of this loss function use the Bayesian personalized ranking, or BPR, which encourages the model to give higher scores to the observed items compared to unobserved ones. The third part of this function is the regularization term. We use the add-on to optimize throughput model. We use the real-world Movilance 100K dataset to evaluate the performance of our throughput model. We employed the evaluation metric recall at sign k and NDCG at sign k to estimate the performance of the model, which are widely used in the recommender systems. In this table, we compare the best result obtained using the selected baseline. Bold scores all the best results in each metric. As it is shown in this table, our proposed model has achieved better results in both evaluation metrics compared with baselines. To verify the effect of multi-layer structure and the use of BPR in finding the similarity in the graph separately, the result of two versions of MLCG BPR-SE, which are named as MLCG BPR-SE-BPR and MLCG BPR-SE-ML, are depicted in the similar to GACSE. The MLCG BPR-SE-BPR approach uses a single sublayer in embedding propagation layer, but uses the BPR to find similarity in node of the same type. Conversely, MLCG BPR-SE-ML employs a multi-layer structure in the embedding propagation layer, but uses the loss function provided in the GACSE model to find similarity in nodes of the same type. As it is clearly shown, MLCG BPR-SE-BPR provided a better output than all other models except the proposed MLCG BPR-SE, which indicates the high effect of using BPR as an auxiliary loss function in improving the model. The lower accuracy of MLCG BPR-SE-ML illustrates the weakness of the GACSE auxiliary loss function in utilizing the high-level information generated in the multilayer structure. Since the scale of the utilized dataset is not very large, it is expected to produce better output in larger scale datasets. However, the effectiveness of MLCG BPR-SE-ML can be clearly concluded considering high accuracy obtained in combining it with MLCG BPR-SE-BPR in the MLCG BPR-SE model. Comparing the effect of auxiliary loss between GACSE and MLCG BPR-SE-BPR using recall at line 20. It is clearly shown that by increasing lambda 1, which means increasing the effect of the auxiliary loss in the overall loss function, the recall results of MLCG BPR-SE-BPR are better improved compared to GACSE model. The effect of number of layers in performance. It is clearly illustrated that the best performance is provided by the model with two layers, and the worst output are obtained employing just one layer. Utilizing more than two layers are expected to provide better results for larger scale datasets, which will be analyzed in future work. Conclusion. In this paper, we proposed a multi-layer structure of graph convolutional network in order to extract effective information to produce more powerful feature vectors. Furthermore, the BPR metric was analyzed and employed as an auxiliary term in the model loss function to extract similarity information related to nodes of the same type in the user-item interaction bipartite graph. We show experimentally that using multi-layer structure and the modify loss function lead to better performance in both recall and NDCG compared to the state-of-the-art approaches. Thank you.